These
errors are there.
yeah. So we are live now, sir.
Yeah.
You can introduce yourself and start the session, sir. So first you can go through those questions and answer. Later on, students.
And enjoying myself. There are some questions about how to do mathematics and also about which books to follow and things like that. So I would like to recommend one by one, slowly build up the idea. So let's see. The first thing is about, the first question is about, sir, suggest few books to prepare for IIT JAM for the topics of linear algebra and functions of 1, 2, 3 variables. So from my point of view, as far as linear algebra is concerned, just look at the following site. Just go to the site. So I'll just show you the site. Alright. Look at this site, home.iitk.ac.in/arlal mth102la.pdf. Alright. If you forget it, just search for my name, Arbind K. Lal from IIT-Kanpur. You will get this home screen. On the home screen, there is a notion, this is called articles in preparation, or you can take math 102A here. Alright, so either wherever you want to click, you can click. Then there are PDF notes. You can look at the PDF note and click.
Yeah, now it is fine, sir. Now it is fine. Let me just click on this OBS Studio, sir. Yeah, fine, sir. Now that Chrome, sir. This one, sir. And then that second tab, sir. Yeah, we are good, sir. Now click here, sir. Yeah, now you can proceed, sir. Showing that Firefox browser.
Alright, so I can show the Firefox. But I have to go all the way again.
No, sir, it is already in Firefox.
It's already in
Yes,
Firefox.
Yes, sir.
Alright. So if you look at, for example, if you want to see, you can see that all these things about looking at whatever I have done in the class, it's already there in this part itself. This was the example which was taken in the class. Alright. These are the elementary matrices that you have here. Look at the questions here. Identity matrix and how do I get those things. And the proof wherever I have left, those are also available here itself. So anything that you want which you feel that is not enough, look at it. These notes will have everything. There's nowhere else to go. You don't need to visit any book other than these notes. Everything is there. If you look at questions also, questions are there about ranks, about system of equations that you can think of, RREF. So just have a look at it, and if you have doubts, even the explaining this example was done in the class, that how do I look at the system of linear equations for the homogeneous system and then the non-homogeneous system. So everything is here. You just have to look at things. Spend some time and nothing more than that. Determinant also, if you look at the determinant here, so all those equivalent conditions are here that you can see that I had done in the notes. All the equivalent conditions here. So 1 to 7 that I have mentioned here, look at this. Those were there in the notes. Fine. Theorem of alternative was also there. Then you just have to find out one. So if A is a square matrix and you have found a left inverse or a right inverse, then the inverse exists. That's also there. Determinant is there. So this determinant is the one that I gave. Alright. I gave all these things, but if you want to look at the actual proof of these things, if you are interested and you come from a mathematics background, then I would like you to have a look at appendix part. So appendix, let me see, can I go to appendix? It's taking too much of time. So is it possible to go to directly to 250 maybe? It will be around 250 or something. Alright, so it's before 250. So here is the proof of all the ideas of determinant. So determinant is being defined here using signature of a permutation. Alright, that's the way we define. And then, so first we define what is called a permutation here. So I have started with permutations, build up on the idea what are the important results there that you need to know. And then I have tried to prove all the results about determinant here, and at the end I have shown that the way we prove it, the way we compute the determinant is the same as the one that's defined mathematically. Fine, so everything is here. Then again, if you look at the vector space W1 plus W2, we define it as a vector from W1 and a vector plus W2, just keep adding, just take any vector from W1 and any vector from W2, keep adding and keep generating whatever set you can. For example, if W1 is x-axis and W2 is y-axis in R2, I can get whole of R2. Alright. Similarly, if you are looking at say xy axis in R3 and the z axis, you can look at their sum and you can get all the whole of R3. Fine. So the ideas are there with you. So those ideas, if you want to look at and understand the dimensions and so on, the proof of dimension I have not given in the notes, I have not given initially in the class also, but you can have a look at here and then do that. So that part is there. Then on the lecture on inner product space and norm, I have said that this parallelogram law is very, very important in the sense that if the parallelogram law does not hold, alright, so I have a norm but the parallelogram law does not hold, then I cannot get an inner product. So here it says that, so there I have given an example also, I think. If not, you can look at the example here or it will be there in the notes. But here we have shown that if I have a norm on a vector space, I also have the parallelogram law being satisfied, then I can define an inner product. I have defined an inner product and I have proven that yes, everything is nice. Fine. So I just would like you to go through them, and as I said, if you want to go for jam, you just have to look at the first 6 chapters here. Okay, so this is this last chapter about eigenvalues, eigenvectors that I am looking at here. Alright. So eigenvalues, eigenvectors. So this is the last chapter. Jam has only syllabus till this time, till this much. Beyond that, there is no syllabus in jam, so you don't have to worry about. This is the part that you should worry about. So just do all the exercises here, you are through. Fine. The next question is from a student. Alright, he or she says that how do people learn mathematics and what teaching methods are most effective? As far as I am concerned, I don't know how to learn mathematics. Alright, I just practice. So I look at problem or I read something. Once I read on my own, alright, once I read something on my own, I try to start asking questions myself. That if this is there, why is this not there? Why is the author or is the person, is the teacher interested only in this, not in this? So we have done a lot of things till class 12th. Based on that, there are a lot of ideas, a lot of questions that we have with ourselves. That when I am looking at functions, then there are a lot of functions for us. For example, sin x, cos x, tan x, square roots. Lots and lots of functions are there. And if you recall in class 12th or 11th, we didn't understand what is called real numbers. Most of us, even most of the mathematicians that we have in India or abroad or anywhere else, we do not well understand what are called real numbers. It's difficult to understand real numbers. We just say that whatever numbers you can create, those are real numbers. Fine. And then suddenly we say that no, it's not enough, because if I look at the equation x square plus 1 equal to 0, then there is no solution of x square plus 1 in real numbers. So on one side we are saying that whatever numbers you can create, they are real numbers. At the same time, I have a system which is x square plus 1 equal to 0, which has no solution in real numbers. And therefore we are forced to go to complex numbers. Fine. So these two are contradictory things, that we are saying that we can generate everything. At the same time, you don't know. Also, where is exactly pi to the power e, e to the power pi? There are a lot of numbers, e to the power e say 100 times, pi to the power pi 100 times, and then I take a square root of that, what happens to that? So all those questions are there that we seldom understand. Fine. But we still have questions that, alright, these are nice, I have understood it in class 12 nicely, can I ask similar questions? So once we start asking these questions, that can I understand something better, our idea just starts to grow. Alright. So for example, as I said, we look at all functions, sin x, cos x, a square root, alright, x to the power 10, polynomials are functions, sine of cos x is a function. Alright, there are lots of functions that you can think of. You can keep on creating as many functions as you want. And then suddenly we are taught that look at matrices in class 11th or 12th, I don't know exactly when, but something like that. The question arises that we are told what is matrix, and what we are doing there is that we look at matrix, look at their determinant, and properties of determinant. Suddenly we get confused, what is a matrix? Is it a determinant or is it a matrix? Because matrix we don't do anything. If you look at it, the definition of matrix is given, special matrices are given, we are told how to compute the inverse of a matrix and how to compute the determinant and then properties of determinant. Suddenly we realize that is it worth reading or is it just for marks? Fine. So it turns out that matrices are nothing but they are also functions from one vector space to another vector space. So what I'm trying to say is that we need to ask question that when I studied matrices, one should ask the teacher or look at the net or somewhere nowadays at least that why are we reading it? Is it just for marks or is it just a mathematical object and hence I've been told to read it so I should read, or I should ask question that from where I have got these things or what is the usefulness of these things. Fine. So once you start asking these questions, you start learning mathematics. So basically mathematics is whatever you have learned, somebody told you till class 12th, just try to generalize those ideas and nothing else. Alright, you looked at differentiation. Fine. We had differentiation in class 12th, that differentiation of x is 1, differentiation of x square is 2x, differentiation of sin x is cos x, then there is notion of integration. All those things were there. Can I do similar things here now? So I have a function from a vector space to another vector space. Can I talk of differentiation of that? Alright. I have a function from f from say R2 to R. Can I talk of differentiation there? Can I talk of any function I take from Rn to Rm? Fine. It may not be linear. Linear is a special one that we are doing, which gives us matrices. But if the function is not linear, what other questions can I ask? Fine. For example, here itself, I have got all linear functions here for us. Fine. Because we are looking at matrices for us, linear functions. Question is that, are these linear functions continuous? Are they differentiable? We never ask those questions. Fine. We need to ask them. We need to understand them. Fine. So this is the idea that if you read something, you ask you questions yourself. Once you start doing it, you will learn mathematics. Because mathematics is, or science for that thing is asking questions. If you ask questions, you are through. Fine. Now, so there is some person who says that they have questions but they have not asked it here. There is one student who has asked that can he write the exam, NPTEL exam in Chatra in Jharkhand. The answer is, sorry to say, that it's no, because at present we just have centers at Dhanbad, Jamshedpur and Ranchi. I think Chatra will be near to Jamshedpur, or I don't know. I was there in Jhumri Tilaiya for some short time, 6 years, but in my childhood, so I don't remember much. But maybe you can learn yourself and you can find out from the net which is the nearest place to go and then do it yourself. Alright. Any other question that you have, please let me know. Please write down and then I would like to answer them. Yes, sir. What is the difference between eigenvalues and eigenspaces? Alright, so if I look at, so what is the difference between eigenspace and eigenvalue? Alright. So the idea is that eigenvalue is a number. Eigenvalue is a number. This number could be either a real number or a complex number, because we are looking only at all the fields which are real or complex numbers as such at our stage. But when we go higher, we have notion of what is called eigenvalues over other fields also. So there again, depending on the field, our eigenvalues will change. So, but what will remain the same is that they will be numbers. Fine. Eigenspaces are vectors or functions. Alright. So when you read ODE or PDE, alright, you will come across your functions as your eigenspaces. And eigenvalues are just numbers. So the basic idea is that, as I said, if I look at matrix, any matrix, so I have to look at square matrices. So if I look at any function f from Rn to Rn, fine, which is linear, which is linear. So linearity is very important. Then this will imply that there exists a matrix M such that f of x is m times x. Fine. So if you look at M here, so M is going to be an n cross n matrix. For example, if I take M to be is equal to, say, I'll just take 1, 2, 5, 7, 7, 8. So 5 plus 2 is 7, 14, 7, 14 minus 1 and 6, 6, 2. If I take this, for example, fine, then you can see that M times 1, 1, 1 will be equal to 2, 5, 7 times 7, 8 minus 1, 6, 6, 2 times 1, 1, 1. And this is equal to just add first column plus second column plus third column. If I add it, I get 7 plus 5 is 2, sorry, 5 plus 2 is 7, 7 plus 7 is 14, 7 plus 8 is 15, 15 minus 1 is 14, 6 plus 6 is 12, 12 plus 2 is 14. So I get it as 14 times 1, 1, 1. Alright. So 14 here is an eigenvalue, and the vector 1, 1, 1 is an eigenspace or eigenvector. Fine. And what is the eigenspace? Eigenspace is nothing but linear span of the vector 1, 1, 1. Alright. So it is just this. Or which is same as alpha times 1, 1, 1. Alpha belongs to R for us. Is that okay? So eigenspace is here. When I look at complex numbers, things could be different. Yeah. So mic, all right, and then go here. Is there any geometrical meaning of eigenvalue and eigenvectors? Yes, there is a very important idea here about geometrical meaning in eigenvalues and eigenvectors. How do we use rank decomposition to solve a linear system of equations? All right, so rank decomposition and this. So first let me answer your geometrical meaning of eigenvalues and eigenvectors, and then we can look at how do I solve it. So eigenvalues, eigenvectors, let me go to my notes. I think that will be much better for you to understand. Yeah.
We need to show us.
Oh, we need to show. All right, fine. So browse here and then go here. Yeah. So in this 6th chapter, I would like you to go towards the end here. All right. Or in the beginning itself, if I look at, I have talked of here lambda here and x here. So my question here was, let A be a symmetric matrix. Consider the following problem. Maximize x transpose AX subject to x belonging to Rn and x transpose x is 1. Fine. So this x belonging to Rn such that x transpose x is 1, this basically is looking at a circle with centered 0, 0. Alright, 0. So I am in Rn, so it is a circle of radius 1 with origin as the center. I am asking that what is the maximum value of this or the minimum value of this. Fine. So the maximum or the minimum value here is going to depend on, so A is here, that the A that I am looking at here, look at the largest positive eigenvalue of A. Fine. That will give you the maximum. And X is basically the corresponding direction. Alright, the direction in which you get maximum amplitude. So I must have drawn some diagram here. Let me just look at it. Yeah. So look at these diagrams here, the 3 of them. So these are corresponding to different examples, A, B and C. So there are 3 examples here. So I must have taken 3 things here for me. Alright. So there is 1 here, 2 here. There should be 1 more. I think somewhere I must have 7, 2 minus 2. Yeah. So this is the third one. Alright. So the important thing here is that look at this first matrix A. Alright, if you look at this first matrix A here, alright, its eigenvalues are 2 plus 1 is 3 and minus 1 is an eigenvector. So 3 is an eigenvalue, 1, 1 is the corresponding eigenvector. Similarly, minus 1 is an eigenvalue and 1 and minus 1 are is the corresponding eigenvector. So you have to, can I write here?
Just directly on this thing?
Yeah.
Yeah, you can proceed, sir.
I can write, alright. So look at this part. I cannot write, alright. So anyway. So what I am trying to say is that there are 2 things here. 3 is an eigenvalue and minus 1 is an eigenvalue. Look at the corresponding diagram now. Alright, I would like you to look at the corresponding diagram. This is the corresponding diagram that I am looking at. Fine. So this line, the green line here in this diagram, corresponds to looking at the vector 1, 1, alpha times 1, 1. So every point on this line, the green line, alright, is alpha times 1, 1. So this line is the eigenspace, the green line is the eigenspace corresponding to the eigenvalue 3, which is the major axis of the ellipse. Alright, and this red line is the eigenvector or is the eigenspace corresponding to the eigenvalue -1. Alright, this is corresponding to the eigenvalue -1 here. Alright, and so here it is symmetric, A was symmetric, 3 and -1 were the eigenvalues. So this 3 is the green line and this is the other one. Fine. Now the next one is, look at the next diagram here. So the next diagram is looking at X transpose AX. So I should have, so no, X transpose X I have already looked at and I have shown you here. So look at this example nicely. So X transpose AX, I have written it like this: 3 times X plus Y whole square upon 2 minus X minus Y whole square upon 2. So you can see that X plus Y here is the major axis, that is, I have not written anything about B here. I have written B here. Where is B? So B is here. Oh. So a small correction now, please have a look at it nicely, a small correction. Alright, since I am talking of ellipse, the eigenvalues have to be positive. Alright, so B has eigenvalues positive. B has eigenvalue 5 and 10 which are positive. So the ellipse has to come from there. So the eigenvectors are 1, 2 and 2 minus 1. So these two lines that I am talking of, this is 1, 2 and therefore it has not come so nicely. Now I understand that this problem is there. Alright. So this line, so I think I'll go back here and write, maybe that's much better. Welcome. Alright. So important thing here for me is that I'm supposed to look at X transpose AX. So X transpose AX is XY here. Then I have a matrix here, say A, B, B, C, because I want this to be a square matrix. So let me not write this. I think I should write here A, H, H, B here and XY here. Suppose I write this. So if I multiply it, what I get here is A times X square plus 2HXY plus BY square. This is what I get. So if you remember, alright, the general conic in second degree was of the type AX square plus 2HXY plus BY square plus 2GX plus 2FY plus C is equal to 0. This was the general conic, alright, and everything was determined by this second order or second degree polynomial. And the second degree polynomial is basically coming from this matrix, which is A, H, H and B. Alright, so you can see that this second degree polynomial has come from here as such and nowhere else. Fine. So it turns out that if the eigenvalues of A are both positive, then we will get ellipse if eigenvalues are distinct, or circle if the eigenvalues are same. Alright. For example, the general conic that we have is X square by A square plus Y square by B square is equal to 1. So look at this part. This part corresponds to XY here, then 1 upon A square here, 0 here, 0 here, 1 upon B square and XY here. This is what it looks like. Fine. Similarly, if I want to look at the hyperbola, if I want to look at the hyperbola, X square by A square minus Y square by B square is equal to 1, you have to look at XY here 1 upon a square 0 0 minus 1 upon b square and xy here. Alright. So this will give you the quadratic type, the conic, the second degree part. Second degree part. So here what I am trying to say is that just look at the matrix. If the eigenvalues are all real, they will lead to ellipse or circle. So depending on the number of negative eigenvalues, you are going to get different things. Alright. So this is what you have to be careful about. Just go back to my notes. Alright. So yeah. Alright, so first thing is that you have understood here. So this is the hyperbola that I have. Alright, the first figure is the hyperbola. So there, this is the line, is this green line is your axis, which is your y equal to x. This is the line y equal to minus x. Here in the case of ellipse, it was, what was that? Yeah. So 2x is equal to y. So y equal to 2x here, and 2y plus x is equal to 1. So they are perpendicular. And this is about a thing which is not symmetric. So the matrix here is not symmetric. Here A and B are symmetric matrices. You can see here that A and B that we chose here was having their symmetric matrices. And the theory says that for these matrices, the eigenspaces are orthogonal. Alright. So eigenspaces are orthogonal means major axis, minor axis are going to be orthogonal. They are perpendicular. But when I am looking at this matrix, for example, this is not symmetric. And for that, I still have eigenspaces for me. So blue line is one eigenspace, green is another eigenspace in this figure, fine. But they are not orthogonal, that is one thing. The most important thing which is striking is that the maximum and the minimum here, the maximum here is going to be positive, which was 3 here, and minus 1, which was negative. In this case, the major axis had eigenvalue 10 here, and 5 was another eigenvalue. So 10 and 5 are the displacement, maximum and the minimum displacements. And those displacements were in the direction of major and minor axis. They were in the direction of eigenspaces. Fine? But in this example C, which is not a symmetric matrix, the maximum displacement is not in the direction of eigenspaces. The maximum displacement is somewhere here. For example, the maximum displacement is this line. Alright? It is along the y-axis. Fine? But the eigenspaces that I have, they are in some other directions. So when I go from symmetric to non-symmetric, the theory changes completely as far as my maximum and minimum are concerned. Fine? So you have to be careful when you do things, that most of the times you look at symmetric matrices. So they are all the axes that you think of geometrically, they will be orthogonal, because every matrix which is symmetric is orthogonally diagonalizable. This is what the theory says, that a statement will appear somewhere here. So let me just show you that the statement will be somewhere. These are the properties, the spectrum of a matrix. Basic results on diagonalization, then Schur-Upper triangulation, spectral theorem. Yes, normal matrices has come. So after that normal matrices you will have this. Let A be a Hermitian matrix. They remark this holds for all the eigenvalues of A are real. So all holds means, so look at this part, remark this 6.4.9. Then there exists a unitary matrix U such that Ui is an eigenvector of A for alpha I. So since A is symmetric, A is Hermitian for us. So these alpha i's will be real numbers. And the Ui's are eigenvectors. So all these eigenvectors U1, U2, Un, they are orthogonal. Why they are orthogonal? Because U is an unitary matrix. U star U is identity. Alright. All these results will hold. That's important. Fine. But as far as the geometry is concerned, I have looked at that geometry part also, which is not in your syllabus, but you can have it, look at it. Quadratic forms. Oh, it's there for you. Sorry. It's there for you, but not at some other place. Alright. So here I have looked at those things. What is a positive definite matrix, positive semi-definite, negative definite, and so on. Fine. And this is the Sylvester law of inertia, which says that if you want to write any quadratic form in certain forms, the number of positive sums and number of negative sums will be the same under certain conditions. So what are called under linearly independent linear forms or under independent linear forms. Fine. So this is the theorem that I was talking about, that number of positives and number of negatives will remain the same. It just depends on number of eigenvalues which are positive, number of eigenvalues which are negative. Fine. And then as an application of these things, I have given you this thing about the general conic here, about the second degree, and I have also done about the third degree here. So x, y, z must have come somewhere. This is 2 dimension here itself, 2 dimension. Yeah, so 3 dimension is here, Euclidean space. So I have given you all the examples of eigenvalues, different, what will happen to eigenvectors and corresponding how the diagrams changes. Fine. Now, camera. First I have to go to the camera. Alright, and then go here. Fine. Is there any geometrical meaning of eigenvalues? So the geometrical meaning, as I said, was eigenvalues was looking at the amplitude. They'll get it, even though I was speaking before.
Yes.
Alright. So is there any geometrical meaning? Yes, eigenvalue is the amplitude. It looks at the maximum disturbance and so on. And eigenvector is the direction in which the maximum displacement and things like that happen. But the displacement are only related with the idea that the matrix A is symmetric. If it is not symmetric, then the displacement will occur in some other direction, which is difficult to compute because things are not nice. Fine. How do we use rank decomposition to solve a linear system of equations? In general, rank decomposition is not helpful. Alright? It is generally not helpful when I am looking at solving system of linear equations. It is LU decomposition which is helpful to us. Alright? Rank decomposition helps us to create examples. Alright? So the basic idea of rank decomposition is, how do I create and understand the theory, that if I am doing something, alright, can I bring it to a smaller example and then build up my ideas. So I have a system in which I need to look at 10 by 10 system. Alright? The rank of the system, or the independent number of components in which I am supposed to look at, maybe only 5. So then I should be able to build up my example with only 5 columns and 5 rows, B and C. So B has, if you remember, any matrix A of rank R can be written as, so A is matrix of size M cross N, then I can write it as M cross R and R cross N. Alright? So I should be able to decompose it into R columns which are linearly independent and number of R rows corresponding to C which are linearly independent. So I can look at 2 different components and I can build up and then question whether what I am trying to explain or what I am trying to infer, does it make sense or not. Alright? So as such, I am not solving a system there, but I am trying to question the modeling that I have done. So it helps in modeling. Alright. So if you remember, look at my first chapter here in these notes, you will see that when I want to create rank 1 matrices with certain properties, I can use those ideas. Fine. So the idea of rank decomposition is basically to question your intuition and build up models. Alright. The next question is, please clear row space and column space. Alright, so suppose I am looking at a matrix A here, which is 1, 2, 1, 2, minus 3, 2, 2, 4, minus 6, 3, 4, minus, suppose I am looking at this. Fine. Or let me write also one more here, 1, 5, minus, suppose I am looking at this. So this is my 4 cross 3 matrix. Alright. Then the column space of A is, I am looking at A times X, and X belongs to R3. Alright. So I am looking at some alpha times, I am looking at alpha times 1, 2, 3, 1 plus beta times 2, 4, 4, 5 and plus gamma times minus 3, minus 6, minus 7, minus 6 and alpha, beta, gamma belongs to R. So I am looking at this as a subset of R4. Fine. And row space, if I want to look at row space of A, it is same as column space of A transpose. So either you can look at, so you can write here, so you can write this as So X transpose, no, so let me not write AX here, so let me write Y here. So A transpose of Y belongs to R4. So I am looking at here in terms of Y1 of 1, 2, minus 3, Y1 of 1, 2, minus 3, plus Y2 of 2, 4, minus 6, plus Y3 of 3, 4, minus 7, plus Y4 of 1, 5, minus 6. And Y1, Y2, Y3, Y4, they belong to R. Alright. So I am looking at two different things. That's what you have to understand. Fine. So there are two spaces, and that is what you need to understand that we get from here. So I would just like to go to one of the videos, not the videos, the file that I have here with me. Alright, so I would just like to go here and show you. I don't know where it is, but it is somewhere. So look at the inner product space. I may have done it there itself because, or maybe I have talked in vector spaces itself. Projections. So it comes there. In vector spaces, last part I think. Application to vector spaces. So here I have defined what is row space and column space for you. What is more important is at the end there is this diagram which I have given you in the notes also. Look at here. So Rn I am looking at here. Here I am looking at Rm. The function is f of x is equal to Ax. So this A is an m cross n matrix. Alright. So what is the row space? What is the column space? I have defined here nicely. And their perpendicularities are here. Alright. So the idea is that something here, row space is here, column space is here. They have the same dimension because the number of rank of the matrix of A as well as A transpose remain the same. So the dimension of row space and dimension of column space will remain the same. But the null space will have different properties because they will have different sizes. But still there are some things nice which are going on. Alright. And I can use these two ideas to get the whole information about the matrix A. That's what it says. If I want to understand the matrix A, just looking at column space is not enough. I have to look at column space of A as well as its perpendicularity. So what are the things that are perpendicular to column space of A? It turns out that all the vectors which are in the left null space of the matrix A are orthogonal to the column space of A. This is what it says. Alright. So that's what is explained here in the, this is the fundamental theorem of linear algebra, and where we talk of that null space of A is same as, look at here, null space of A is equal to column space of A transpose, or perpendicular to, this is perpendicular to the column space of A transpose means row space of A. Alright. And then you can interchange it also to say that null space of A transpose is equal to column space of A perp. So this transpose here will get shifted to a transpose here, that's all. Alright. So they are related, all those ideas are related. This is what it is, fundamental theorem of linear algebra, and I have stated it here. That null space of A transpose is perpendicular to the column space of A whole perp. Alright. So if you want to understand, either you can understand null space or the column space in some sense, but that does not give you all the information about the matrix. It gives you some information but not the full information, because if I want to create models, if I want to create examples, I need to understand them so that it makes sense for us. Alright. So these theories are basically to understand and build up models. Alright. So building models are more important, and therefore we need to look at those models. The next question is row space, column space. I hope you have understood row space and column space. If not, please just go there. Build up the examples yourself. If you can build up the examples, everything is done. How are fundamental spaces obtained? By using linear span. The linear span of what vectors in RREF or original matrix gives the specific fundamental spaces. Chat disconnected. Please wait while we try to connect you. Successfully connected. Alright, so let's see. So you are asking about how do I get from there. So let me just go back there again. So vacuum here. Alright, so here for example, so I have this matrix A. When I compute RREF of A, look at this matrix. This matrix has the property that, so I have the one that I have constructed here has this property that, so if I, so if I look at this 1 1 1 here, alright, just add it, you will get here as 0 0 0 0. That's the way we have constructed it here. Alright, so the rank of this matrix, rank of A is 2, fine. And in this example you can see that the way it is, it should look like, the RREF should look like this. There are 4 components, so it will be this, and there will be some things here that I do not know what they will be. Alright, so this part says that look at this row and this row. These rows have been obtained from initial rows of A. Alright, so not in this example, but if I look at this example, understand it nicely. I can look at 1 1 2, 2 2 4, 3 3 6, 1 4 8. Suppose I look at this matrix. Alright, so this is my matrix B. Let us compute, apply the Gauss-Jordan method for us. So I will just apply the Gauss elimination itself. What I will get is 1 1 2, 0 0 0, 0 0 0, 1 minus 1 is 0, 4 minus 1 is 3, 8 minus 2 is 6, I hope. Alright, so from here I can build up my 1 1 2, 0 1 and 2 here, 0 0 0, 0 0 0. Alright, so I have not got the RREF, but I have got the REF here. These are the 2 pivots that I have. Fine. So it turns out that from here I can conclude that this implies that this column, so this row comes from first row of B, and this has come from the 4th row of B. So this implies that the first and 4th row of B are linearly independent. Alright, so they are the basis. So the basis of this is 1 1 2, and so the basis here will be this, comma 1 4 8. So this will be the basis as far as the row space is concerned, because the rows are generated by these rows. Row space. In case of row space, I can also say that this is also equal to, so the linear span of this is also equal to linear span of 1 1 2, comma 0 1 2. So I can do this also. They are same, that you can show yourself, because this is the way we have obtained here by multiplying by elementary matrices, which is playing with the rows of the matrix B. Alright, so they are same as such. So I don't have any issue from where you had come, that you can understand, because this part I am written basically because this will help you in understanding when I look at the row space of A plus B or A intersection B and things like that. At those places these ideas help, that from where they have come. Fine. But when I want to look at the column space here, then I have to look at the first column and the second column. Then you can show that the column space of A is generated by, it is a linear span of 1 2 3 1 and 1 2 3 4. This is what you can show. Fine. It is not this. So this is not equal to linear span of 1 0 0 0, comma 1 1 0 0. It is not. Fine. Here it turned out for the row space it happens because I am applying row operations. Fine. So this turns out to be true. So here it is true as we are using row operations. Fine. Here this is not equal, alright, not equal as we are not using column operations. Alright, you can just say that pick up the columns corresponding to those pivots. Alright, look at those pivots from wherever they came, from whatever columns they came, those pivotal columns, they will give you the answer. Alright. AC थोड़ा सा कम कर
Yes, sir.
दीजिएगा.
I did, sir.
All right, thank you. Sir, very nice and clarity ideas. Thanks, sir. How do we obtain a basis for a vector given the vector space itself? Possible to explain through an example. All right. How do we obtain a basis of a vector space given the vector space itself? Possible to explain through an example. Yes, it is possible to do it through an example. So there are two ways of doing things. One is, there is this theorem which says that given any finite dimensional vector space, alright, so given any finite dimensional vector space, just look at the first non-zero vector, alright. If it gives you the whole space, then you are done. That vector that you chose, which was a non-zero vector, is linearly independent, and that is a basis. Or if it is not the whole space, then I should be able to find a vector which is not in the linear span. Alright, then the new vector and the old vector, they will become linearly independent. So let me again go back here, vacuum. So what I am trying to say is that I have a vector space V, alright, that's given to me. So pick a non-zero vector from V. Fine, you can pick it, it's possible, if V is not just the zero vector. Alright, if V is LS of U1, then this implies that this set U1 U2 is linearly independent subset of V. This theorem is there. If you look at the notes, this theorem is there that at any stage, if I am picking a vector which is not in the linear span of the previous one, then the new vector is linearly independent of the previous ones, or the new vector is not in the linear combination of the previous ones. Alright. So this theorem was stated in the theorem. So I can get this. So if linear span of U1, U2 is V, then this is a basis. Else, pick U3 belonging to V minus LS of U1, U2. Fine. So this will again imply that U1, U2, U3 is linearly independent subset of V, and that's the way that we go. Since we are taking that it is a finite dimensional vector space, so this process has to finally end. So the idea is that at each stage you have to pick something which is not in the linear span of the old set of vectors. So my first set of vectors was 0, so I am picking U1. Alright, my original vector is 0. You understand that every vector space has a 0 vector in it. So I am not picking 0, I am starting with something which is different from 0. That is possible only when V is different from 0. Alright, so I can pick this one. Once I have done it, I look at whether I get the whole space or not. If I do not get the whole space, then I should be able to pick U2, which is not in the linear span of U1. It turns out that in that case, by the theorem that we have done in the class, U1, U2 is linearly independent. If I get the whole space using U1, U2, I am done. If I am not getting the whole space, means I should be able to pick something. So I can pick something. Again, they will become linearly independent, and I can build upon those ideas. All right, that is one way. The other way is solve the system of homogeneous system. So I've been given that. So sometimes I am given something like this, that V is a vector space consisting of some x, y, z, w, v belonging to R5, so that x plus y plus z plus w is 0, y minus 2z plus v is 0, and something is given, some conditions are given to me. So solve this system, so get a solution set of the homogeneous system A of x, y, z, w, v is equal to 0. Sorry, there are only two of them. So get this solution. Alright, the vectors that you are going to get, that will give you the answer. Fine. So it just comes from this part that since there are two linearly independent here, so you should get three vectors in the basis. This is what it happens because there are two linearly independent equations here. That is one way of looking at it. The other way is heuristic argument, that you just pick so that things are nice. So you can pick here if you want. So this idea tells me that there are two of them. So I can pick vectors here which is 1, minus 1, 0, 0, 0 because there are 5 components. So I need 5 components here. Fine. So I've taken care of x and y. But here see this condition is not being satisfied. So there is a problem here. So this is wrong because I need the vectors from here itself. Alright. So I need to choose my things nicely. So 1, minus 1, 0, 0. And this has to be satisfied. So again I have to take this. So this will be there, one of them, because minus 1 plus 1 will be 0 and z is 0 for me. I can take another one as 1 and then I can take z here. So if I take z here as so 0 here, minus 1 here. So if I look at this, what I get here is that y is 0, z is minus 2 times z is 2. So I should put here, I think, 2 here. No, I should put minus 2 here. So minus 2 plus 2. So this will be there. And you should be able to get a similarly with w also something. And then done. So 1, 0, 0, y and z. W should be here. So minus 1 and 0 here. So all the three conditions are satisfied. You can see here. Fine. So y and z are 0. V is also 0. This is 0. So I think this is the correct answer. So this is forms the basis. So this is by a heuristic argument. And this is linearly independent basically because I have taken them to be so. So there is a look at these three. Alright. These three part. So this third part, the second, third and fourth components, if you look at, they look like minus of identity matrix. So this is minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. They look like this. Alright, so they are linearly independent. Fine. So that's what is important, that you can build up those ideas. The next question, how do I obtain a basis? Please throw some light on the left null space. So basically there is not much in the left null space. If you have understood the null space of A, then the left null space is nothing but null space of A transpose. Alright, please understand. If you have understood null space of A is all vectors x such that A times x is 0. Fine. So left null space is all y in Rm such that A transpose of y is 0. We are just multiplying on the left. Alright. Or which I was just saying that if I am looking at things here, so I have got A here which is m cross n. Multiply on the left. So by y, so y times A transpose or y transpose A is 0, which is same thing as looking at, so I have got A is m cross n. So there are two ways of looking at things. One is looking at A transpose. A transpose will give you an n cross m matrix. So I can look at A transpose y, and y belongs to Rm. I can look at this. So this will give me row space of A. Fine. If I want to look at the left null space, fine, then I am supposed to look at A transpose all y such that A transpose y is 0. I am supposed to look at this part. Alright. And what is null space of A? The space of A is all x such that A of x is 0. Fine. So I can also, so basically problem is that I am writing left null space. Basic problem is that all my vectors are column vectors. Alright, so hence my vectors should look like columns. Fine. But I can also think of this in terms of, so what I'm trying to say is that I can look at Y transpose such that Y transpose A is 0. Just look at this part. If I look at this part, take transpose, so look at A transpose Y is 0. Alright, Y such that this happens is same as looking at Y transpose such that A transpose Y whole transpose is same as 0 transpose. I'm taking transpose everywhere. Alright, that's all. So then this is same as Y transpose such that just multiply this out, you get Y transpose A is 0 transpose. Alright, so it should be a transpose here. So because the row vector has to be the row vector. So in place of, we do not write like this basically because all our vectors are column vectors. But here I am saying in terms of row vector. Because Y transpose corresponds to a row vector. Alright. So this idea left null space is same as this space itself. They are same. The only difference is I do not write this because of the problem with my initial notation or the initial notation that is followed by all mathematicians, all in some sense, is that our vectors are column vectors. Alright. If there is no confusion, if you are sure of your what is row or what is column, things like that, you can take one of the notations and do all your work. There's nothing special about it. It depends on you. You are good at it. You can do things on your own. How can I get this note? Which note are you talking about?
I think whatever you are writing now, sir. We will
Yeah.
upload, sir. We will upload.
Alright, so whatever I am writing, it will get uploaded on the screen or on the website itself. So there is no problem. And as far as my lecture notes are concerned, you just search for my home page. On that you will get everything. Alright, just search for it, you will get everything. Find at the above link. Sir, where is the link? I don't know where is the link, what link you are talking about. But if you want to go to my home page, so just a minute.
Or else we can copy that link, sir, in the chat itself.
Oh,
Sir, can you go to the browser, sir?
Welcome.
Firefox, sir. Firefox. Here, sir.
here.
Copy this link, sir. Yeah, copy. And then let's go to that Chrome, sir. Not that, sir. This, sir.
Here.
Yeah, here. This, sir. Let's paste the link here, sir. So that, yeah, paste. And then submit, sir. They can view that link, sir.
So I have sent you the link of my notes. Alright, you can just download from there and understand. But it's for you is only till chapter 6. Alright. And if you want to understand little bit of this SVD, then there is something there. I have not yet completed the SVD part. Fine, but it depends on you. But there are some other things also which are there, which are very useful in applications. Alright, about symmetric matrices, about non-negative matrices and so on. I am from non-engineering background. I am a doctor. I have not studied mathematics for past 6 years. Alright, that's good. You are coming to mathematics, you are learning mathematics. The main reason for joining the course is to get the clear idea for machine and deep learning. I feel hard to study the course, so can you help me how to study the course? Excel myself in concept for ML and DL. Also tell me the chapters to focus mode. So what I will say is that for the time being, you should not worry about linear transformations. What you should understand is the matrix multiplication. That's very, very important. So you should learn the first chapter so that you are confident of my notes. Once you are confident of my notes, alright, so just concentrate on the first chapter. That is the matrix multiplication part. Then there is something about submatrix. You just give a glance and move fast. Then go to the second chapter and then try to understand the rank decomposition, alright, and the results on invertibility, RREF, invertibility. You don't have to know the proofs, you just have to understand that there are a lot of conditions which make the same statement, but they are different languages, alright. So basically, when you go from one subject to another subject, the languages change, alright. So therefore you need to do that. So the first thing is that you should understand matrix multiplication. The next thing you should do is understand the rank decomposition and the invertibility conditions so that you can make sense of them. Determinant is not so important for you. Then you should go to some inner product but not understand the full of inner product. Just try to understand some inner product, that is the dot product for you, and then the row and column space, the fundamental spaces that you should understand in vector spaces, and then go to eigenvalues, eigenvectors of symmetric matrices. For you, for ML and DL, you will need things on what are called SVD. SVD, I have just given you the basic idea of SVD. So you should learn some SVD, but all the idea of SVD comes basically from symmetric matrices. So just let me write that part for you so that you can understand. I have explained it just simple, but if you want to understand, have a better understanding, just spend some time and you will understand. It's not difficult. So if you want to understand SVD, what is called singular value decomposition. So the idea here is that I have a matrix A which is M cross N. I want to write it as some S, D and some T here. So I don't know what were notes what I followed here, but I don't remember it. This is M cross N, so this is M cross N for me. So this is M cross M, T is N cross N, and S and T are unitary matrices. Alright. So I want to write A as this. If you look at the proof, basically I am using here, so if A is this, let me compute what is A times A transpose. A times A transpose will be SDT times SDT transpose, or let me write a star here because I cannot do things here, so let me write a star here because I'm saying unitary here, so a star. So this is same as SDT into T star, D star, S star, which is same as SD T times T star, D star, S star, which is same as SD D star, S star. All right. So DD star, so DD star are the eigenvalues of A times A star. All right. And S is the unitary matrix in the spectral decomposition of Hermitian matrices. Alright, so let's understand again. So what I'm trying to say here. So I know that if I look at this matrix A times A star, this has the property that A star whole star is same as A star star A star, which is same as A times A star. So this matrix A star is a Hermitian matrix. So I can use the spectral decomposition. A spectral decomposition means go to the eigenvalues and eigenvectors part. There is a notion of what are called normal matrices. They are diagonalizable. So there is the spectral decomposition, which tells that every Hermitian matrix can be decomposed as unitary matrix times a diagonal matrix and U star of that. So this and so U is unitary, D is diagonal. Alright, so this is what I have done here. Alright. Similarly, so S comes from decomposition of A star and T will come from, similarly you can check that, similarly if I compute A star A, I'll get it as SDT whole star SDT. So T star will come here, then D star D will come and T will come. Alright, so you can get S and D using these ideas, fine. But somehow it becomes a bit complicated if you want to understand it this way. What we do, alright, so generally this is not given in most of the books, but I would like you to understand this, that what we would like to do is that A is m cross n matrix. Alright, if A is m cross n, either m is greater than n or m is less than n. Alright, if A is greater than n, I can build a matrix B which is m is bigger. Alright, so it is m cross n matrix. I can build like this. I have A here, I can put extra zeros here. Alright, now once I put extra zeros here, so B is a nice matrix which is a square matrix. So B is a square matrix. Fine. And then I can look at B plus B star, or I can look at BB transpose or B transpose B, and then work with this. Is that okay? If I work with BB transpose and B transpose B, both are symmetric matrices. And therefore I will get something nice, and that I can use. This is one way of looking at it. If m is less than n, then I can build a matrix C. Well, I'll have to add extra zeros here. Alright? So that it will become n cross n, and I can do with this. Fine? So to understand it nicely, in general it's difficult to understand using m cross n. So you patch up with extra zeros so that you have a square matrix. And for a square matrix, you know all the results, and therefore you can understand them nicely. Is that okay? You just have to remove certain rows and columns, because this extra padding, so you'll have to remove something from your unitary matrices to build up your ideas. Is that okay? So that's the way to go about it. So for you, Santosh, you need to understand matrices, that is a matrix product, little bit of vector spaces, but you must understand what is the row space, column space, that is fundamental spaces related to the matrices, eigenvalues, eigenvectors, how do the unitary matrices behave, and once you have understood eigenvalues, eigenvectors, then you can go to SVD. SVD is the most important thing for you. If you go down the page, then your handwriting is not visible in the screen. Somebody says that.
Anyway, we will publish it as a PDF, sir.
Alright, so my notes, whatever I have written here, from next time I will not write below, but it will be published there, so you can see it on the website or something. But from next time I'll not write it that way. Alright. Any other question that you have? I cannot see anything else. Chat disconnected. Unable to connect to chat. Please try again later.
It's working, sir.
Huh?
Let's refresh, sir. Let's refresh the page, sir.
Refresh the page.
Yes, sir. Let's see. Advance, sir. Let me just see, sir. Some kind of internet connectivity issues. Yes, sir. It is available later also, sir.
If you have invertible matrix, then we get entire space. How? Alright. So the question now is that if I have an invertible matrix, then how do I get the entire space? Let's try to understand what does invertibility means. Invertibility basically means that all my columns are linearly independent. Can you say that part yourself? Can you think about it? So there is this set of conditions that I have in my notes, or that I have done in the class also. So I need to go here, then browse course, go here. So let's go back and see here that system of equations. Yeah. So look at this thing, a square matrices with linear system. Since you are saying that it is a invertible matrix, so it has to be a square matrix. This theorem says that A is invertible if and only if RREF of A is identity. Alright? Not only that, look at 6th. It says that the system AX is equal to B has a unique solution for every B. Or look at 7th. The system AX is equal to B is consistent for every B. Alright? Now this system says that, now you have already said that A is invertible. Since A is invertible, so the system AX is equal to B is consistent for every B. So whatever vector that you want to choose from your vector space, alright, I can solve. So I can solve the system, given that A is invertible, I can look at A times X equal to B has a solution. Whatever that solution is, that will give me the linear combination to get me B. Is that okay? So if x1 to xn is the solution here, then x1 times the first column of A plus x2 times the second column of A plus so on till xn times the last column of A will give me the vector that you are looking at. Is that okay? So you need to understand this nicely here. It says that A is invertible if and only if the system AX equal to B is consistent for every B. Fine. So your question here was, let's look at that part. So your question here is, if you have an invertible matrix, then we get entire space. Alright. So understand, it will depend on what invertible matrix that you are talking about. If I have got Rn or Cn, n cross n, and the matrix A is n cross n invertible matrix, then yes, I'll get whole of it, because as I said, A is invertible means the system AX is equal to B has a solution for every B. And getting the whole space means what? I should be able to get the whole space as the column space. And getting the column space means just looking at linear combination of the columns of A. So which is same as AX. AX is x1 times the first column plus x2 times the second column plus so on till xn times the last column, the nth column of A, which is giving me B, which is the whole space. Fine?
Yes, it will be.
Yes, so there is this question that does this live will be available on the YouTube later? The answer is yes, it will be available. Will be
The not chats on the other parts, like the video parts.
The video part will be available.
Yes.
Any other question that you have?
So it is time, so we can find out if
So I will wait for 1 more minute. If you don't have any question, then I would like to stop the chat here, live session itself. And if you have any doubts or anything, just send the mails. My TA will reply to you. And if still you are not comfortable, just write again. Alright? And ask the TA to contact me. Fine? I'll do that. Don't worry, I'll answer all your questions. Alright, let's wind up then. Thank you.
So, we want another session at the end of the course, so we can have sir.
Yeah, sure.
Yeah. So,
See, you can have the session whenever you want. If you are not comfortable, if you want session, I'm always available. So don't worry about the availability.
right, sir.
Alright? So, I will be available.
We will fix a date and time later on, sir. Maybe after a week or so, we will fix a date and time, sir.
For the chat letter as well. Fine?
Yes, sir.
So the time we will decide after some time, maybe 2nd or 3rd week of November or something like that.
Right, sir.
Fine?
Sure, sir.
Because the first week of November I have some work that I need to do, and after that I'll be free. So maybe I can do that afterwards. Alright?
Sure, sir.
Fine? Thank you then.